Hello, this is part 2 of my electric vehicle charger project. In the previous video, which I will link below, I have built this charger on a piece of plywood. In this episode, I will put it into an enclosure and make some changes in the process. I ordered a couple of enclosures on eBay. This one is very similar in size to one of the OpenEVSE enclosures. Look, there is this rubber cord which goes into this groove to make the enclosure waterproof. So I ordered this one first, and then I found another one which is slightly smaller. It's a bit longer and it's very similar in size to the Nissan charger I have. Let's compare them side by side. Each enclosure was about $16, including shipping from China. And I will try to fit my charger into this one. I really like it. It's gonna be a challenge, and for this I will certainly need a smaller power supply than this. One of those 12-volt supplies I showed in the previous video, combined with a 5-volt regulator. So here I took this supply apart and compare it with the supply I was using so far. This one is quite a bit smaller, and this one is 12-volt 1 amp supply, which should be plenty. And the output voltage was a little low, it was 11.6 volts, so I had to adjust it. I was almost sure it must be possible. And when I opened it up, I found that this package is a classic 431 adjustable shunt regulator. Here is a small part of the circuit I traced. It's just enough to understand how to adjust the thing. The minimum voltage is achieved when this reference input is connected to the cathode, and the maximum is achieved when it's connected to the anode. And the way this thing works is by feeding back through this optocoupler the difference between this point and this stable reference voltage. So to adjust the output slightly higher, I needed to adjust this reference input voltage on it slightly lower. So one way would be to remove this 1K resistor and replace with a slightly smaller resistor, but I decided to do it another way by putting some other resistor in parallel with this one, lowering this resistance a bit. And after a few tries I found that putting 27K resistor in parallel increases the output voltage from 11.6 to the target 12 volts. And here is this resistor I soldered in parallel with this surface mount 1K resistor, and it's a precision resistor. We don't really care about how accurate is the resistance because I manually selected it anyway, but what's important is the temperature stability of the thing. Usually precision resistors are more stable in this sense than regular ones. Back to the breadboard. I have made a few changes here. Well, first of all, I moved things around to make room here. So I moved this pilot op-amp, and instead of optocoupler here I have just an inverter which is transistor based. Just to remind you, this is to pretend that both AC lines respond when a relay driver pin goes high, AC sense lines go low with this little jumper. Both go low, and the microcontroller believes it's a level 2 connection. So I'm using this 12 volt supply and this isolated DC to DC converter to produce negative 12 volt rail, and this 7805 regulator to step down from 12 volts to 5 volts and produce 5 volt rail. And here I added MCP23017 I2C port expander, which is needed to connect this LCD display. And here I added a button, which is select button, to make the menu selections. And this is done according to schematic for the LCD module from the OpenEVSE project. Now let's turn it on. There you go. We should be able to make changes. For example, this max current setting. Oh, plus 10 amps. What does this mean? Oh, it seems like that plus means it must be the current selection. But why? 24 amps is the default. And now I don't even see 24 as an option. That's weird. Let's select 25. And let's exit. Now let's talk about the 5 volt power rail. This LCD has very efficient modern backlight, which takes only about 15 milliamps. But I have another similar display which is older, and the backlight is not as bright as this one, but it consumes about 160 milliamps. So in this case now, the overall current on the 5 volt rail probably will be a few tens of milliamps. It's not a complete circuit here on the breadboard. There are a few extra things like an op-amp for GFCI and a couple of opto-isolators for AC line testing, but they shouldn't make a significant difference. So I hope that this 7805 regulator shouldn't get too warm. As I mentioned in my previous video, because the voltage drop on the 7805 regulator is 7 volts, it can get quite warm if the load on the 5 volt rail is significant. For example, in a case when LCD display has a backlight which consumes 160 milliamps or something like that, and it's not a very good idea in a completely sealed enclosure. So in such a case, switching step down converter can be used, and I showed this candidate from DigiKey. It costs $5.50. However, I found an alternative like this on eBay, and it costs 99 cents including shipping from Hong Kong. So it is a step down adjustable converter. Here is a tiny trim pot on it, and the output can be adjusted from 1 volt to 17 volts, and the input can be from about 5 volts to 23 volts, but the input always should be higher than the output. And according to the seller, it can run up to 1.8 amps with 3 amp spikes. But I will not go into details in this video. I'm going to make a separate video about them. And for now, in this charger, I'm going to use 7805 and we'll see how it goes. I also bought this current measurement transformer so that the actual current can be shown on the display. I couldn't find the schematic of the measurement circuit in the documentation section of the OpenEVSE site, but I found it in forums in one of the discussions. Here it is, and it's quite simple. And the output must be connected to one of the ADC inputs of the microcontroller. And let's check. So this is the pilot, and I have a diode and a resistor here to pretend that the car is connected and charging. So, and here the current should be displayed, and now it displays a noise, and I can find which input pin the measurement circuit should be connected to and connect it to the ground to see this noise disappear. There you go, I found it. It was pin 23, ADC 0 input, and I connected it to the ground, and there is no noise now. Here I implemented the changes on the board, and here is how it looked before. I removed the LEDs connector which was here because we don't need LEDs anymore, and this connector is for the display, and this connector is for the current measurement transformer. So this trim pot is the burden resistor. So this schematic to measure the current is generic, and here this burden resistor is shown to be 56 ohms, but as I learned from the forum, in our particular application, given the type of the current transformer and the range of the currents we are going to measure, this must be 22 ohms. So these two resistors are just the offset, half of the power rail, and these parts are just to limit the current and limit the voltage on the output to the microcontroller. So I'm using this 50 ohm trim pot as the burden resistor, and unfortunately the adjustment is on the side. I would prefer it on the top. This one is going to be hard to adjust when the board is in the enclosure. And this connector is for the button, and it has 3 pins because the button I ordered has a blue LED built into it, which is not really necessary, but nice. And because we will make 5-volt rail from the 12-volt rail, this 5-volt connection is not going to be used anymore. I didn't want to change the connector just for that. And here's the other side. Let's give it a go. In particular, I want to see how warm this regulator gets. Now we have the full system, so the test failed, of course, and let's wait for a while and measure the temperature. Alright, this thing was running for about 15 minutes, so let's measure the temperature around this regulator. Okay, and I see this maximum of 33 degrees C. And let's measure the ambient. Ambient is 21 degrees. So it's running in the open air at 12 degrees above ambient. It's gonna be a little worse in the enclosure, but it's looking just fine so far. And let's measure the power supply just in case. Alright, I see the same 33 degrees on the power supply. And let's remember that the power supply was already completely enclosed in this tiny plastic box before, so we shouldn't be too worried about the power supply. So here I'm powering this thing from the precision power supply, and we can see that it consumes 69 milliamps, and almost all of that must be on the 5-volt rail. There is that tiny current draw by the DC to DC converter, which is producing negative 12-volt rail, but it should be negligible. So let's assume that 70 milliamp current is flowing through the 5-volt regulator, and the voltage drop is 7 volts. We multiply that and we get 0.49 watts. So the 5-volt regulator has to dissipate around half a watt, which is not too bad. Just a quick test of the current measurement. So I put the board back on this piece of plywood prototype thing with the same previously used power supply, from which only the 12-volt rail is used, and it's plugged into a regular outlet, level 1, and the car is charging. And I already adjusted the trim pot so that the reading here, 11.9, agrees with the kilowatt meter. Here I mounted most of the components on a piece of board. It's gonna be very tight, but it looks like it should work. So there is just enough room for the display and the button and GFCI transformer. And these are strain reliefs I picked up at a local hardware store for $2.50 or something like that. We are almost there. Everything just barely fits into this enclosure. Let me show you the progress. I prepared this frame, which I made from a piece of plastic, which I saved from an old printer I took apart some time ago, and I usually keep pieces which have flat surface, so I can use it for precisely such occasions. And I'm going to put it like so. The nuts will go on this side, of course, and here I'm going to glue in a piece of transparent plastic, perhaps something like this. Here is the result. It's fully assembled, except that the cover is held by the rubber bands, and this is because I want to quickly check the temperature after more than half an hour running at 16 amps. Let's go. Let's start with the 7805 regulator, and it's running at about 39 degrees C. What about the relays? Relays are running at about 55 maximum, and the power supply I see 56 maximum, which is a bit more than I hoped, but not a problem. And the ambient now is 19. And finally, a finished charger. Thanks for watching, and my big thanks to the OpenEVSE project developers. Goodbye.